Okay, so in today's lecture, we're going to talk about one of the extremely popular algorithm in machine learning. It's called decision tree. It is very popular in a lot of applications. So here is the basic information about the decision tree. Later on, we're going to introduce the algorithm, how to construct the decision trees with the various methods. So the first thing, like decision tree, is you can think about is it's defined by the hierarchies, and the hierarchies are rules in form of trees. And I believe you have seen the data structures trees before. So I mean, decision tree is also can be considered as like a data structure of trees. It it has like basically it has a rule from the internal nodes. These rules actually test the value of some features of this data. For example, whether it's a bigger than certain threshold or smaller than some like certain and a certain threshold. If this threshold is satisfied with the true, it goes to one branch. It is like false, it will goes to another branch. So this is very straightforward. Just it's and it's binary tree here. Root, which is the topmost internal node. It's a tree, so this will be the root. You can think about the trees as like this. So this actually here is the root. The decision tree node at the end of these right here is the leaf. So everything like in the middle right here, that's internal node. Okay, so this just give you like different part of definitions of a tree. So the whole idea of the learning is we want to construct or fit a decision trees models. And once we have a trained decision trees, we can and can be used to predict a new input. There are a lot of good advantage of the decision trees. It's very easy to interpret because everything is white box. Precisely where should I put this and put this like decision tree and put this and to the left branch or right branch, and everything to make the prediction is super quick. So for example, this is one of the examples I'm using right here. So this is right here. So, and you can think about this is a very simple examples. The root node right here is body temperature. The key here is we want to distinguish whether an animal is mammal or not mammal. So basically, I have a two leaf node. One is mammal, one is non-mammal. So there are like internal node is the give birth or not. So the root node is whether the body temperature. If the body temperature is cold, it will be non-mammal. If it is warm, it will ask whether it gives birth or not. If it doesn't give birth, it's non-mammal. If it is give birth, that will be mammal. So this is very clear rules that will be followed. It's basically how a biologist will make and the predictions whether this animal is mammal or non-mammal. So give a logic sense how they think. So this decision tree is it's very close to the intuitions of scientists. So that's why a lot of people like to use decision trees in practice. Okay, so let's go back. And also here I want to give one simple examples that I want to classify a 2D points that in blue and green or the two features. So basically this is 2D planes I want to classify. So, and you can see everything here will be blue, and everything here will be green. So I want to classify everything into and blue green. And obviously this is not linearly separable perfectly. I mean, it's not that straightforward to do so. And what you can do right here is, in fact, you can, create decision trees look like this. So basically, it starts with the rules that if x2 is bigger than 5 or not. If it is bigger than 5, it will goes to right branch. If it is less than 5, it will goes to left branch. So this is just like, this internal node and to make the prediction. So basically this actually separate on the x2 right here. Horizontal on the like horizontal axis. And they are going to make differences on the vertical axis on x1 right here. So basically, if x1 is bigger than 8, it will be green. If it is less than 8, it will be blue. If it is like less than 2, it will be blue. If it is greater than 2, that will be green. So this, actually basically partition this whole and the whole like and space into bunch of boxes. And this actually boxes, so point and within those boxes will be and predicted as the corresponding and the class, whether it's a blue or green. So basically, this is exactly how the decision tree is doing. It's basically making the predictions by partition the whole space into a bunch of boxes. Okay. So you can see, so the whole idea of this first node that we have is we want to check whether this this feature is greater than certain threshold. If the yes, then we ask whether the second feature is greater or less than the threshold or not. If both are true, then we are going into the bottom left of the leaf. This corresponding to the the region of space which is x1 is bigger equal than t1 and x2 is bigger equal than t2. So basically we are basically partition, as I said, partition the whole 2D spaces into these 4 regions. If the data is more complicated, we can use like enough split to have a like deep enough trees to make all these and partition on these spaces into many regions. If we have a D layer of the trees, in general, you can have a 2 to the D of partition of the whole spaces. All right, so you can think about and what we're actually doing is right here, we are making this and this is my decision boundary here. And I want to let you know this is very different from the decision boundaries that you would think in SVM or logistic regressions. In all these cases, these things just being and smooth functions. Here is just being boxes. So this is my decision boundary. Yes, decision boundaries, and you can actually make this piecewise linear approximations of decision boundaries if you have a more complicated shape. But before like 2 layers of the decision trees, you and this is my decision boundaries, which is like and basically and a couple rectangular and boxes. So mathematically speaking, is we're actually trying to make this estimate by doing and by getting this weight as so like W. One is basically the weight of like all the yi in these regions, and it divided by the number of the and by the total number of the data. And then this regression just being the and the weighted sum for the values on each boxes. So this is basically you can think about is it's called regression trees if we need it. So basically, if like things here, it's not and classification, it's blue and it's not blue and it's green. It's just some like and a very specific functions and a certain like continuous values. We can still do it with the decision trees. And what we can do is we can just trying to using one constant to and to approximate the values in that boxes. And obviously that would be very crude, but in some like argument that would be the best possible approximations. So this is just, and it's nothing but the weighted sum of my target, and this is basically the weighted average on this target in one specific boxes of R1, and then the whole region is being partitioned, and you sum them together for all these constant and on each corresponding locations. For example, you can think about right here, you can think about we are trying to do the partition like this. So this will be R1. So so regions, the value, and the value that on this R1 will be basically the value of X, fx will be W1, right? So this is basically similar ideas of the regression, but we are just using piecewise constant to approximate the functions. And Rj is the region that's specified by the jth leaf node, and the Wj is predict output for the node. But the parameter that we have for this problem is Rj and the Wj, right? All right, so that means we need to find out the corresponding boundaries, and for each boundaries and for each boxes, we need to assign the values, whether it's blue or green or certain like continuous values in the regressions. So as you can see right here, and the decision tree here can work on classifications and regressions. So it can work on both. Depends on like whether y and my y is discrete or y is continuous. Right? If it is continuous, it's basically we're working with and with the regressions. Okay, so that's one toy examples. Another toy example I'm going to show you is the following. This is the toy example that we want to decide whether we want to play tennis or not based on the 4 features. One is outlook, one is temperature, one is humidity, and one is wind. They are all category input. So, for example, this is a table that you are getting here. We have a data of 14 days. For outlook, it can be sunny, it can be overcast, it could be rain. For temperature, it will be hot, mild, and cool. For the humidity, that will be high, normal. And the wind, that will be weak and strong. And the play is yes or no. So basically, we have 4 features, and I want to predict whether I will play whether I will play tennis or not. All right. So you can see everything is categorical input. It has like all bunch of different and sort of quick and features. So if you actually look the decision trees being created in this like situations, you find out we're only using use 3 features out of 4. The first feature that we use is actually the outlook. So basically, if it is outlook is sunny, overcast, or rain. If it is overcast, that will be yes. If it is sunny, then we check the humidity. If it is high, that will be no. If it's normal, that will be yes. If it is wind, rain, so that will check the wind. If it is strong, that will be no. If it is weak, that will be yes. Okay, so now the question is, So I have two questions. Why we have to test outlook feature first? And also the temperature feature is completely ignored. So the whole idea is this outlook is the most informative out of 4 features, right? And also the temperature is not informative. So I'm keep like saying this word informative. So that means we need to quantify this informativeness mathematically. What do you mean by this whole thing is I mean this feature is more informative and another feature is not informative at all. Right. So if we can understand this, then we can construct the decision trees. Okay, so let's just formulate the math a little bit. In terms of math, we still have this training data set, which is xi and the yi, I from 1 to the n. X is a vector. And the key here is this x right here can be continuous, can be discrete. Previously, we always assume this x is in the Rn or Rd, but in this cases, this x can be categorical, right? So this can be discrete. So this is quite different. Can be categorical. So, and also the dependent variable, so which is my target, can be and also can be continuous and it can be like discrete as well. Depends like what kind of the problem that you are working with. So we will use the training data to construct the decision trees. And of course, each internal node will corresponding to some rules to test some features. To fit some model, that means we have our predictions, and then we have the target right here. And again, we're going to come up with some loss functions. And hopefully, if these two are close, then this loss value will be small. If they are like far away, then they will be, so the loss function will be large. So this is tricky because we're basically using piecewise functions to approximate my yi right here. So like in general, this is basically says we have a yi here, but the value that we predict is wj for all the xi in the region of like rj, then we sum them together. Right. So basically for all the region in rj, I'm going to predict the value being wj. Okay, so but we know for piecewise constant functions, one of the big issue is this is not differentiable. So that means I cannot take partial derivative of L theta with respect to theta here. That's not possible. That we cannot learn this discrete tree structures at all using gradient informations. So that means everything that we learned from the gradient descent here is it will not work as when we construct and trying to construct this decision trees here. But we can do something slightly different. So this whole idea is we are going to using this greedy and procedures. Then we basically iteratively grow the tree and at one time. So the whole idea is coming as here. The highly informative features is going to place higher up in a tree. So that means if we have some feature has a highly informative, I will put in the root or something that is much higher. Tree. If it is less informative, I will put on the lower levels of the trees. Again, we need to find a way to rank these features. So here are the couple methods I want to talk about. The first one, it's called like iterative dichotomizer. It's for short is for ID3. The second method is called classification and regression trees. It's called CART. So these are really, really popular and algorithms and has been used for like 30, 40 years already. We're going to dig this in details and actually implement from scratch. All right. So the key here is what kind of way that we're going to quantify whether this feature is highly informative or not. So in ID3, we are going to using something called entropy and information gains as a criteria for the rankings. Okay. But in all my feature here is like categorical and discrete, and my output is binary. So these are my assumption here. So my assumption here is my feature is all categorical, and all like categorical, and my output is binary, just plus and minus. And we are using entropy and information gains as the criteria and for rankings here. So, and how this is done, and let me just step back to introduce what is the entropy in the information theory right here. So, I mean, entropy here is basically, it's like measure the randomness of the data right here. And for example, if we have, a set of S for the K classes, this will being like associated with some like multinomial probability distributions. You should be very familiar with this an expression right here, P1 to Pk, and we know each component here, Pi, it will be between 0 and 1, and the sum of Pi that will be equal to 1. So this just to indicate this is a probability vector. The entropy right here is defined as follows. It's basically sum and the sum of like Pi log Pi, and this logarithm is based on 2 instead of E. So this to indicate we are working with a binary and rather than the logarithm. So for example, if we have the situation of the probability equal to half and half versus 0.3 and 0.7, the first entropy it gives me is equal to 1. On the other hand, if for this one, it's approximately equal to 0.88. So that means this half-half contains more uncertainties than 0.3 and 0.7, which makes sense, right? Because for the second probability vector 0.3 and 0.7, it's more likely to be on the 0.7 part. On the other hand, for half-half, it's like has more uncertainty and it has like, and it can be anyone on the first one or the second ones. Right. So this is very intuitive. This gives you some idea that to measure the randomness or uncertainties in the data. So there are certain properties, very important properties. And the first thing is this entropy is always bigger or equal than 0. So like no matter what, this is like, and it's always a part like non-negative quantity. And actually the minimum is reached when and one of the Pi is equal to 1. So that means as I'm certain, like the probability, and this will be on the ith class. So that means there will be no certainty, and all the instances are coming from the same class. So this is the situation that I have, say, 0, 1, and the zeros, right? So and everything else is just being zeros, only one entry being 1. In this case, I have no uncertainty, and that means my entropy is actually equal to 0. The maximum is reached when Pi equal to 1 over K for a class. That means it's uniform distributions. That means it has maximum randomness or maximum like uncertainties in terms of the data. So so as a general remark, if you have a bunch of probabilities or probability distributions, if you have a more like equal probable classes like uniform, it's more likely to be high entropy. If you have a more dominant or skewed class, that means it's more likely to be low entropy. So as a result, you can think about, I mean, even with the distribution wise, for the distribution that with the and the Gaussians with like low variances here, this is like more like low entropy part because we know the, I mean, and the probability is mostly concentrated around the mean. On the other hand, if you have a like Gaussian that has a large variances, then that will be the higher and entropies because the uncertainty is higher in these cases. All right. On the other hand, there will be something called information gain. So here we're just talking about the entropy, I mean the randomness. So the information gain is basically the entropy of the set of S subtract the entropy of S conditional on the value of the feature F. So this is something called conditional entropy given the value of feature F. So that means if we know the feature of F and what is the entropy and of the set of S now. So this is something called information gain of S comma F. So basically, if you know this information of the feature, how much say if we know the value of F, how much information can I gain from that? So this is basically measure this informations. So this basically, if this information gain is high, that means F feature is more informative. If this information gain is low, that means my F is less informative. So as I said, this is actually measures the decrease in terms of uncertainty about the set of S once the value of feature F is known. So that means, and once we know these features, how much uncertainty has been decreased. So this conditional entropy can be and actually compute as the weighted sum of the as entropy of each separate set, and this is the subset that which feature F is having the value of F. So basically, we are going to partition the S into bunch of and a subset of and SF. Within this SF, this features F have the same value of F. And this line right here actually denote the number of element of the set, right? So this is basically like and pretty straightforward right here. And here, okay, the reason that we call this way is because we have to multiply the probability my feature F equal to the value of F. So this probability is nothing but cardinality of SF divided by the total number of S right here. Okay, so you can see this is quite straightforward, and I mean in terms of the calculation, this is nothing just but like counting all these and the features and the values. Okay, so let's see what we have. Okay, so I think we can finish up here. So so right here, so we have, and for this tennis examples right here, I want to see we should have 9 plays and 5 no plays, right? So we have 1, 2, 3, 4, 5. So this is 5 no, and the 9 is being yes. So in terms of this S will be the days, which is from 1 to 14. Then we have a 9 play and the 5 no play. Then the entropy right here will be, and the probability is 9/14 and the 5/14. Right, so the entropy that we got is about 0.94. So that's the uncertainty that we have if we just have no idea about as other features, this is basically that amount of uncertainty that we get. The first thing that we consider is the wind. I mean, in terms of the wind, we have strong and weak. So these are the two possible cases. I mean, in terms of features, there will be 6 of that it being strong, and 8 of that is being weak. Right, so 8 of that is being weak. I mean, in terms of when for the 6s being strong, there are 3 play and 3 no play. That means the entropy for this set right here is just being 1, right? Because it's half and half. So this is basically half and half. So the entropy will be 1. This right here, we have 6 play and 2 no play. So this is 3/4 is being play and 1/4 is being no play. So the entropy, for the set conditional on wind is weak is 0.81. So then my information gain for the whole set on the feature of wind, it's nothing but HS, we already know, then subtract the conditional entropy as on the feature of wind. So this is being calculated as follows. So we have 8/14. So that is the weak set, and multiply by 0.811. The strong one, which is 6/14, and multiply by 1. So you can show this information gain here is always bigger equal than 0. So you can prove right here. I didn't prove here, but you can prove that information gain is always bigger equal than 0. So there's no way the second term is bigger than the first term. So you can prove this part. So that means give you the information gain right here is 0.048. So basically, if you happen to know your wind, whether it's weak or strong, the information gain is simply 0.048. So we do this for all the features. Then we get this amount of information gain, and you can see from the information gain, this outlook has the most information gain. So that's why. That's how we quantify this feature is being more informative than other features. So we choose this feature as being the first features on the root node. Okay, so that's why we choose the features of outlook that 9 is being. So we have and 3 possibilities. One is sunny, one is overcast, and one is rain. And out of this sunny, there will be 2 plus and 3 minus. For the rain, there will be 3 plus and 2 minus. But for the overcast, it's always plus. So that means we have reached the root, which is yes. So the information gain right here, information that we got is 1 and 0. So that means the entropy here is and 0 right here. So we cannot further reduce the entropies because that's already the minimum that we can get. We have absolutely no uncertainty in that. In these situations. So then we're going to remove this outlook. So that means that we're going to remove this features. There are 3 more features need to be determined the order. So we need to grow the trees. So we have already determined this is my first layer of the tree. So we need to grow the trees. Just second layers or even further. So then, for the left and the node, we have these 1, 2, 8, 9, 11 with 2 play and 3 no play. If we set this is my set of S, then we can calculate this entropies. This is 2/5 and 3/5. The entropy is about 0.97. Then we have like 3 more features. We have a temperature, we have humidity, and we have a wind. Again, for the feature of temperature, we have a hot, we have a mild, we have a cool. This is 1 and 2, this is 8 and 11, this is 9. With that, we have 0 play and like 2 no play, and 1 play and 1 no play, and 1 play and 0 no play. So that means for the first one and the third one, they are all deterministic. So this like entropy is actually is 0. The second one, for the mild, that will be 1 play and 1 no play. So the entropy is still equal to 1. So then you calculate the information gain conditional on the feature of temperature. This part and this part, they are 0. The only thing actually contribute is when the temperature is mild, which is 2/5 and times 1. If we subtract that, we are getting the an information gain is 0.57. Similarly, we can do all the other 3s and other 2s for the humidity and wind. In this cases, we're going to choose the and humidity because this has the maximum information gain of 0.97. All right. So for the middle node, we already know there's nothing to grow. It's already there's no randomness here. For the right node, you do the similar things. In this case, you are going to choose the wing. And after that, you find out and everything on the node is already deterministic, right? So there's no more randomness. If it is, left branch with the humidity, whether it's high or normal, I'll always give you, deterministic yes or no. For the right branches, for the wind, whether it's strong or weak, it will give you deterministic no or yes. So basically, there's no more randomness in these cases. So we will end and stop our growing of our decision trees. So we go back and we find out this is our stopping criteria. So this is basically stopping criteria. That is, all the training examples have the same labels, right? So basically, and it's being perfectly fit our training data. So there's no errors. Or we run out of features to test. That means we will have some training errors in these cases. That's basically we try all possible features, but turns out that there's and still there's no way to separate certain and a certain set and for the plus or minus. So this is whole idea of the ID3. So basically, we first compute entropy of the data set, and for each feature, we're going to calculate the entropy for all categorical values. And we calculate average information entropies for the current features. So this is basically the H of S, and this is H of S conditional on the feature of F. Then this information gain is H of S subtract H of S conditional on F. So this is your information gain of F. So you do and loop through all possible features and pick the highest gain features. Then you repeat until you get the trees that you wanted. All right. So that's basically the whole algorithm. This whole algorithm is pretty straightforward. And in the next lecture, we're going to actually implement this from scratch. All right, so that's it.